Today I will be presenting our work on debating a little where is the responsibility for concurrency control, and specifically concurrency bugs, really isolation violations perhaps should be a more appropriate term, and to what extent we can rely on developers, to what extent we should do this automatically. The work was done by three undergraduate students then, Chaoyi, Mingzhe, and Nuo. They have all since graduated, went on to pursue graduate studies. This leaves me as your speaker. We wanted basically Wang, who's our distributed systems colleague, present this work, but his visa didn't get through. So you're stuck with me. What is basically the main motivation here? As has been long observed, there's a gap between how developers think about their applications in this serializable transaction model, where there's no worry about concurrency, the database system will just take care of it, and the reality that most applications don't use serializable transactions. That again is long known. Andy Pavlo had this wonderful keynote, maybe 6 years back now, where he showed examples from a survey of DBAs, where they pointed out that the most common isolation level was read committed from memory. Just last year at Sigma, there was this paper that was studying ad hoc transactions. That is, applications that actually create transactions through other mechanisms outside of the database system, things like external locking or external versioning. So by now we know that this is actually happening. What kind of concurrency bug are we interested in? A very simple example here, which actually mimics exactly what was shown before in the talk. An application developer writes the following statements. It checks if the quantity is positive. If it is, in the same transaction, it goes and takes one out. That is the developer's implementation of buy one item. A little while later, the developer comes back, files a report and says, my unit tests always pass, so it's not my code clearly, but when I run your database, quantity is sometimes -1. Tell me what's going on, something isn't going right. Well, that will get resolved as not a bug for the very simple reason that under the default level of read committed, the following execution can happen. Transaction 1 can read 1, transaction 2 can read 1 at about the same time. Now, the update part comes in, transaction 1 goes ahead first, grabs the write lock, brings the value down to 0. Transaction 2 is blocked. Once transaction 1 gets done, then it's transaction 2 turns. It correctly bounces quantity down to -1 and commits. And hence, from a database perspective, this is a correct execution. It's exactly what the application wanted. That is precisely the kind of isolation bug we are looking at here. What we did is we basically started by looking at, I will start and present a study of concurrency bugs in real world applications, focusing specifically on going deeper than just reporting the bugs. And I will conclude with some thoughts on what can we do that I hope build on the tools that basically left us by the previous talk. Let's start with a study. What did we end up, basically, why did we do that? We started by asking the question, do those weakly isolated or ad hoc transactions cause anomalies in real applications? Or is every speaker just cherry picking one bug and showing it to us? And in total, we have 3 bugs. We just have many different papers around them. Second question, how much effort does it really take to handle those anomalies? If developers have to fix it today, how long does it take them? And finally, which was a big curiosity for me, why people don't just do the obvious, bump up their isolation level to serialize it? What are they worried about? And a lot of speculation there on the answers, including contention is not high enough, things can be manually fixed because business processes will take care of it. Maybe fixing this is easy, right? And hence, we shouldn't really be focused on that. Those are the questions we started and set out to answer. What's our methodology? And I want to basically be careful here because, again, our study is directly influenced by how we approach this application and created this list. We investigated active, that is active with recent commits and activity, not just releases of code happening on GitHub, active open source applications that have a database backend, largely from the e-commerce, gaming, chatting, and ORM tool domain. We started by basically inspecting bug reports, then went to discussions to understand how those bugs were fixed and what discussion took place to fix them, and actually look at the commit history to see how the code changed. It was very hard to nail down a specific keyword or phrase. we started by going really broad, searching for things like SQL, transaction, read committed, race conditions, and so on, and had to manually inspect through a lot of hits that basically keyword search gave us. In this study, we ignored deadlock-related issues unless they are specifically related to the isolation level. What we ended up doing is we look at 46 different open source applications, found 93 isolation bugs, for which one tried to classify the consequence, the root cause, and the fix for each bug. Full list, if you want to extend the study or critique our approach, you can find it here. It's just a long spreadsheet where you can take you through direct links to every single instance we identified and how we actually basically classified it. What is the key limitation? One of selection bias. Let's all keep this in mind. We have only looked at open source applications. That was the obvious place to look at as academics. The corollary of that, which was not immediately apparent when we started, is that this also means most bug reports pertain to behaviors of open source database systems. There is the keyword search limitation. We may be overrepresenting behaviors that can be described very succinctly, things like crash, exception failure, which are fairly straightforward to report, or fixes like select for update. For update is easily keyword searchable. We may be missing bugs that are described in basically other terms or often in domain-specific terms. Take the example from the previous talk. A user registered for this forum twice. No single keyword in that phrase would probably match our keyword search. We would search for duplicate, right? So that's a limitation as well. And of course, as with every study of this nature, we cannot really conclusively answer what is the percentage of applications that experience concurrency issues. We just know it is a significant number based on this study. Let's start and take each basically outcome piecemeal. First, what are the consequences? How do those concurrency bugs manifest? Most common one is inconsistencies in the data. Wrong count, basically inconsistencies take, but almost 80% of the issues we found. Wrong count and miscounting, undercounting, or overcounting alone is 30 out of those almost basically 90 cases. That includes things like double spending, overcommitting basically an item, drawing below your inventory, and so on. Another big problem, and much bigger one in fact, is duplicate IDs. Cases like the bug described in the previous talk will generate in duplicate entries. Those are particularly tricky for the following reason. Very often, the application logic is written in a way that assumes only a single item will return, yet correct SQL execution will return any item that matches the predicate. Meaning often you will end up basically looking for your orders and actually find out basically either one, which confuses everybody. Those do not occur in mostly idle applications, right? Sorry, those occur in mostly idle applications also, which was a new insight to us. Say, systems that have about 100 orders per day are sufficient to trigger a bug, which was idle by any standards from a high-performance transaction processing crowd. What are the root causes here? Mainly, read followed by relevant write is what the main cause is. 42 of them, almost half, are versions of exactly what I showed before. An if check and an update happening within the same transaction, not recognizing the possibility of an isolation violation there. Another 10 are actually variations of that now operate on basically they read and possibly write different rows. An example is select the max ID and increment one, right? You read everything and just add one, and this gets inserted twice. Inappropriate handling accounts for some others. Interestingly enough, overhandling can cause that as well. And in a few cases, we actually saw unnecessary concurrency. That is, a transaction was really meant to be basically executed as a sequence of transactions, yet by issuing those in a standard basically programming language, those ended up committing in a different order than they were issued by the application. And the interesting part here is this was flagged as an isolation bug by the developers, yet no isolation level provides any kind of order guarantee, which was interesting to us. How developers fix those bugs? Turns out there is no universally acceptable solution. Select for update accounts for a good fraction of that. That is forcing the lock-based concurrency engine to do write locking for those reads. Adding a constraint is a very common fix for basically uniqueness violations. The next two, additional locking and additional versioning, are really efforts to develop concurrency control on the side. Checking before commit closes some isolation, basically violation gaps, such as the case I showed before. You can always check that quantity is positive at the end of the transaction, otherwise abort. but otherwise doesn't resolve the core issue. In some cases, they opt for serial execution, changing the isolation level, usually to stronger, those 7. In one case, once they strengthened it, they found out that they had timeout problems, and then they reverted to weakening the isolation and breaking it apart to multiple transactions. And then exception handling causes more, and the others category is really things that were either open when we hit the bug, or that basically we could not directly attribute to just one issue. To quickly answer the questions, do those happen in real applications? They do. How much effort does it take? A lot. And I hope the previous talk also convinced you on that. What we actually saw is that the biggest step of the effort, with some luck and tricks to increase the conflict rate, you can get it to reproduce usually. Fixing and verifying is even higher. It takes often multiple rounds. Maybe the first fix causes other issues. It takes often weeks or months to close an issue for good. Why not serializable? In short, the answer is log locking. And I will not elaborate here, but I'm happy to talk more offline. And finally, let's talk about what can we do. Short-term solutions, basically, are to actually point out, obviously, to database systems that implement different forms of concurrency control, have different features. Things like snapshot isolation, unique or auto-incremented IDs. Those would go a long way towards addressing some of the uniqueness violations, or optimistic concurrence control, right? It could convert some of those isolation violations into aborts. However, for the reasons that have to do with the specific applications we targeted, we have some discussions to prove that this would likely be dismissed as a non-starter. This is influenced by the methodology in the following sense that it is usually unlikely that the open source application, basically, which is again provided to users at no charge, would actually basically be backed by a non-open source database, right? We're not looking at a tightly integrated solution. We're really talking about applications where the users and the data store and the actual code come from different entities, right? So that, we speculate may have been basically the reason for this gap there. And do note that stronger isolation or better implementations of concurrency control will not address all problematic behaviors. Things like duplicates, assumptions for transaction ordering, again, will be prevalent regardless of whether you use Postgres or Oracle. An interesting research direction ahead, we think, is automatic program analysis. And a colleague on the PL research side basically is very excited about this opportunity. Consider the following 2 transactions on rows ABC. A write to A followed by read to B, transaction 2 writes A and reads C. What will current systems do? Lock-based concurrency control will block, waiting for the right lock on A. Optimistic concurrency control will execute both transactions, detect a conflict, abort one. Yet, if you carefully look at how I constructed this execution, an automatic analysis tool can easily determine that this execution is always serializable because the operations can interleave in any order and still maintain serializability. Thus, it is theoretically possible for this narrow case of those 2 specific transactions to actually run with no concurrency control. No concurrency control star, because transactional locks may not be needed, we still need latches to ensure the atomicity of the write to A, right? So no to transactional locks, but still yes to latches. And here's where it gets interesting. Could source code analysis really identify those no concurrency control necessary points? Essentially boiling down to when isolation can be guaranteed by query semantics. If you can get that, we know from recent research, I recall, for example, this paper at from Wisconsin by Jignesh Patel group at VLDB last year, where we can convert this transaction execution basically under a scheduling problem and solve very efficiently, as long as we know the predicates of every query. What would it take us to go there? We want basically to make sound static analysis precise, which we know is a struggle. A lot of those applications are in dynamically typed languages that are really hard to analyze precisely. Even the state of the tools is not as advanced as, say, languages that are strongly typed like C. Extracting query predicates from SQL is non-trivial. This is largely even for vendor-specific reasons. Things like if I have a nested query, right? Does the inner query, can I assume that I'm reading the same basically timestamp as the first one or not? This is highly vendor specific. No vendor will basically explicitly commit to a certain way to implement the concurrency control kernel. Yet this is necessary for us to understand queries at this deeper level. And finally, as with any such study, there is some tension between the abstraction of a concurrence control model, which has power in its generality, but it is limited in its precision, and doing something that is vendor specific, tied to particular implementations. What is the problem? That problematic behaviors on a model may not manifest because the actual application concurrence control constrains the execution in a different way, and vice versa. Problems identified on the actual implementation may appear as non-issues under the formal model. What are the opportunities here? Again, corroborating what we heard from the previous talk, the application logic in all the cases we saw is actually extremely simple by at least the standards of what program analysis today considers as modern programs. It is very often has no multi-threading, instead it has a very simple multi-process model, does not really stress the scalability of static analysis tools today. In addition, in all the cases we saw, there is no persistent data sharing. There's no even data sharing at all happening at the application logic. This eliminates a large source of imprecision due to understanding, again, accesses to shared objects, shared heap objects, which is a very hard problem and a source of imprecision for many static analysis tools today. So we're optimistic that those two, in some sense, point to a promising path for automatic analysis. Continuing, how can we incorporate developer effort? And that is perhaps part of what the database community can basically help with more. Again, developers will always be able to convey insights or basically constraints that automatic tools will never be able to extract. Things like transactions that we can relax consistency for. For example, TPCC has a transaction that can be executed in a delayed fashion and doesn't need full serializability. It can specify things like no concurrent accesses from the same client, only one card per user, as Amazon.com has, and similar constraints. The question there is, how do we actually presenting those concurrency bugs in an understandable way? State-of-the-art approaches show you a complex graph with dependencies between nodes. It takes probably much longer to understand the graph than it is to actually understand what is going on. Can we do better? How can we incorporate user feedback on this abstraction? Can we automatically suggest modifications to SQL that would actually fix the bug in application code? Those are really exciting questions that we see no easy answer. Finally, this is my last slide. As I'm the academic, basically, again, as a subset of Unirumar, it also asks a question about developer education. We noticed that universally, people are a lot more comfortable at the programming language level rather than the database level. Specifically, we noted the widespread use of the term race condition to describe those issues in bug reports. That is really not basically, again, the term database people would use for what is an isolation relation, right? That comes from distributed systems and multi-threading programming communities. Naturally, the first reaction is saying, let's add a lock to constrain the execution. It is easy to understand, yet probably very hard to get right. Yet, if we are to more formally introduce isolation earlier in a curriculum, we run into other problems that first, operational definitions of locking, think of the Gray et al. Papers, say, grab a lock, then release at the end of the transaction. That really is basically points to a specific implementation. Dependency graph-based definitions are more modern, but again, understanding them and explaining them basically takes a lot longer. With that, wrapping up, I presented a study of those real-world concurrency bugs. Overall, we saw 93 bugs from 46 open source applications, and I left with some thoughts on what can research do, largely focused around the automatic analysis path, and what abstractions we need to create to allow, again, user input in this really tricky aspect. Thank you, and I'm happy to take questions.